Welcome to the Transistor Tutorial Series, Episode 2, the Bipolar Junction Transistors Introduction and Large Signal Model. In the previous video, we calculated the properties of a simple bipolar junction transistor, or BJT, circuit that can amplify voltage and demonstrated its various properties on a breadboard in the lab with a 2N3904. In today's video, we're going to continue with the BJT, first going over the basic structure, discussing the three operating regions, introducing the central equations of the large signal model, and finally briefly discussing the broader question of why transistors are so useful. So, what is a transistor? A transistor, at its most fundamental, is a voltage-controlled resistor. The voltage between two of its terminals, the base and the emitter, controls the resistance between two of its terminals, the collector and the emitter. However, this is somewhat inaccurate because the controlled resistance is very nonlinear. It's actually a lot more accurate to say that a transistor is really a voltage-controlled current source, with the caveat that the current source cannot provide power. It only operates in such a way that the applied voltage drop across the current source results in dissipating power, not generating power. This means some other power source, like a battery, needs to supply voltage to the transistor so that it can draw current from that power source. So, like a resistor, the transistor can only dissipate power, not generate it. But unlike a resistor, the current is mostly independent of the applied voltage. This all may sound a little confusing. I'm finding it difficult to do the very initial introduction of a transistor, especially while avoiding getting too deep in the physics. I think the more we talk about transistors, the clearer their operation will become. That's why I made the first video in this series more experimental and less explanatory. Putting a transistor on a breadboard and messing around with it for a bit is the best way to start off learning about transistors. So now that we have the sort of bird's eye view of what transistors are, let's dive a little deeper into their structure and operation. So, there are two main types of BJT, NPN type and PNP type. They are named like this because of the configuration of the N and P type semiconductor materials that make them up. The differences between the two types of transistors are difficult to articulate without understanding the basics of how they work. However, learning about how to use one type is very easily translatable to the other type. They're sort of like mirror images of each other, so all you have to do is flip a few voltage signs and current flow directions to convert between them. We'll talk about the different use cases for each type in a later video. For now, let's focus on the more common of the two, the NPN type BJT. All equations, current flow directions, and voltage positive or negative signs after this point will assume an NPN transistor unless specified otherwise. Here we have the schematic symbol of the NPN transistor. It has three terminals, the base, collector, and emitter. I've also noted that there are three currents, the base current into the base, the collector current into the collector, and the emitter current out of the emitter. The transistor is made up of three distinct semiconductor regions that are all contained within the same semiconductor crystal. The regions have the same names as the terminal names. The collector is a lightly doped N-type semiconductor region, the base is a lightly doped P-type semiconductor region and is quite thin, and the emitter is a heavily doped N-type region. So we see that while at first glance the structure looks symmetrical, the significant difference between the collector and emitter doping concentrations indicates that it is not. You might look at the structure and note that diodes are comprised of PN junctions as well, and that this structure looks like back-to-back diodes. And in some ways it does behave like that, especially when the base terminal is not connected to anything. But in most ways it behaves quite differently because of how thin the base region is, the fact that there are no semiconductor-conductor junctions separating these two PN junctions, and all three regions are contained within the same semiconductor crystal. A deeper discussion of how BJTs work from a semiconductor device physics point of view is very useful for advanced circuit design, but at this stage of the tutorial series, it is more of a distraction. We'll revisit the internals of the transistor in a later video once we've gotten through more of the basics. The voltage between the base and emitter controls the collector current. For the NPN transistor, the higher VBE is, the greater IC is, and vice versa. The current that flows into the base is small compared with the collector and emitter currents, and so the transistor also provides current gain. However, there is a caveat to this. The transistor will only work like this properly if the terminal voltages are within certain ranges relative to one another. The relative voltages between the base, collector, and emitter give rise to what we call the operating regions of the transistor. And to properly understand and use BJTs, we must first explore what the different operating regions of a BJT are. There are three main operating regions for a BJT. In each of these regions, the transistor exhibits different behavior. So before we start analyzing any circuit with a BJT in it, the first step is to identify the operating region so we can apply the appropriate formulae. The first region is called the cutoff region. Here, for the NPN type, both the collector and emitter voltages are higher than the base. The line in the diagram indicates the terminal with the lowest voltage. In the cutoff region, the transistor is fully off. No current except for a very small leakage current flows through the collector terminal. The transistor's collector-emitter junction is considered effectively an open circuit. In the forward active region, the base voltage is above the emitter voltage, but still below the collector voltage. In this region, the transistor is on and is capable of high gain and is therefore the best region for analog circuit amplification. The collector current is well defined and does not depend significantly on too many parameters. So it is relatively easy to calculate relative to the saturation region, which is the third operating region. In saturation, both the base collector PN junction and the base emitter PN junction are forward biased. There is very little gain available, and the collector current is much less straightforward to calculate. The collector-emitter voltage is very low, and so in some cases it can be thought of as a closed circuit or a short circuit state. For most analog circuits, we'll be designing the system to be operational in the forward active region, occasionally design it to be in cutoff when we want the system off, and avoid saturation, as that is rarely a useful operating region for analog design. So for now, we'll continue our discussion assuming the transistor is always in the forward active region unless otherwise noted. So now we present the common approximation to the Ebers-Moll model for the forward active region of the BJT and its central equations, which make up our large signal model. Here we have collector current equal to IS multiplied by e to the power of Q times VBE over KT minus 1, where IS is the reverse bias saturation current of the base emitter junction in amps, Q is the charge of an electron in coulomb, VBE is the base emitter voltage, that is, the voltage of the base minus the voltage at the emitter, in volts. K is Boltzmann's constant in joules per Kelvin. And T is temperature in Kelvin. Note that IS is highly dependent upon temperature, which is worth noting even though it is rarely written as a function of temperature, in spite of temperature appearing as a parameter elsewhere in this equation. The second equation in our large signal model defines the relationship between collector current, emitter current, and base current. The base current is effectively a kind of leakage into the base that is proportional to the collector current. This leakage is captured in a parameter called alpha, which is equal to the ratio of the collector current to the emitter current. We won't discuss where alpha comes from right now. We'll save that for later videos. To get an equation for IC in terms of IB, we first recognize that IB equals IE minus IC by Kirchhoff's current law, and with these two equations, we do some algebraic manipulation and see that IC is equal to alpha over 1 minus alpha times IB. This quantity, alpha over 1 minus alpha, we define to be the parameter beta, which is effectively the current gain from IB to IC, and sometimes called HFE, especially on transistor datasheets. The range of values for beta for a given transistor under different conditions is provided in the transistor's datasheet. It is worth noting at this point that while we tend to treat beta as a constant with respect to collector current, it actually varies quite widely. For the popular 2N3904 transistor, which we used in the previous video, beta varies from 30 to 300 depending on the collector current, part-to-part variation, and other factors. However, we'll see later that we can design our circuits not to rely on the precise value of beta, but more to rely on beta being large, which renders this wide variation immaterial. So, looking back at the first equation, we see that there's nothing in that equation that indicates why it's commonly said that transistors don't turn on,
until VBE equals about 0.6 volts or 0.7 volts. So what's going on there? First, we need to know the common range of IS for silicon NPN BJTs. So, most silicon NPN BJTs have a reverse bias saturation current in the range of 1 femtoamp to 1 picoamp. For power BJTs, it may be higher, but as most transistors are in the signal range, this statement stands. So let's take a look at a chart of VBE versus IC for the low and high ends of this range. So we can see here that even though IS has a wide-ranging value, varying by a factor of 1,000, for most reasonable IC values, which is 10 microamps to 1 amp for almost any signal-oriented circuit, VBE only produces those IC values from about 0.4 volts to 0.9 volts. And this is why it's commonly said that the BJT turns on at around 0.6 volts or 0.7 volts. Another part of this is that while almost all signal BJTs have between 1 femtoamp and 1 picoamp of reverse bias saturation current, a significant fraction of these have a narrower range of between 5 femtoamps to 100 femtoamps, and so the 0.6 volt turn-on makes even more sense there.
So these are our two central equations that govern the operation of BJTs. We have an expression for IC in terms of VBE, and an expression for IC in terms of IB. So, with these equations, we can set VBE to a value, and we can determine IC, IE, and IB from that. The only circuit parameter we're missing is the collector voltage. So how do we determine collector voltage? Well, effectively by omission, the large signal model indicates that the collector voltage does not affect IC, IE, or IB, and so the collector voltage is determined by whatever voltages and impedances are connected to the collector. This makes the system look like a voltage-controlled current source, where the collector current is controlled by VBE and is unaffected by changes to the collector voltage. It is not immediately clear how this is useful, so let's see conceptually how we can make use of this behavior with a few simple circuits. So first, we construct perhaps the most obvious circuit, grounding the emitter, connecting a variable voltage source, which we take as our input voltage, to the base, and connecting a static rail voltage to the collector. Collector rail will be set to plus 12 volts since that's a common enough voltage source. So we can increase and decrease Vin, and the collector current will change by the exponential equation in the upper right. The base current will be significantly less than the collector current by the factor beta. So while this circuit demonstrates what happens, it is wildly unexciting since the only voltage that changes is Vin, and that has nothing to do with the transistor. Things get much more interesting if we put a resistor on the collector. Here, with RC between the plus 12 volt rail and the collector, changing Vin now changes the current through RC, which in turn develops a voltage drop of VRC due to Ohm's law. VRC is equal to the resistance of RC times the collector current IC, so it's equal to RC times our central exponential equation.
So what can we glean from the relationship between VBE and VRC that is of importance? Well, first, let's look at a plot of VBE versus IC to give us some perspective. So here's the exponential. Now we need to think of this circuit in terms of signals rather than just voltages. In this case, let's set our input signal as a change in voltage of VBE rather than just the total voltage. This is important because, as we can see from the plot of current, it's best if we can apply an offset voltage of about 0.6 volts before applying our input signal so that we can get significant collector current. Similarly, we set our output signal to be the change in voltage of VRC. This eliminates any offsets caused by the VBE offset we apply on the input. So, looking back at the plot, we can see that at low VBE, we can see that the slope of the curve is more gradual, so the change in IC over the change in VBE is small at that point. And thus, the change in VRC over the change in VBE is similarly small, since VRC is proportional to IC. At higher VBE, the slope is steeper, and thus the change in IC over the change in VBE is higher, and same with the change in VRC over change in VBE. The exponential nature of the collector current means that increasing VBE will increase the slope of the collector current. This theoretically goes on forever, though obviously it is restricted in practical situations. What this all means is that for large enough VBE, the change in VRC over the change in VBE will be greater than 1. This means the circuit applies voltage gain. A signal of a certain amplitude input to the system will become a larger amplitude on the output.
However, voltage gain is not exactly special. Transformers, for example, do not require semiconductors, and they can produce voltage gains. While technically they cannot produce DC gain, they can still produce AC voltage gain. So what sets the transistor apart from the transformer? To answer this question, we have to think about the power in and the power out. First, we think about power in. We know from before that at least with something like the 2N3904 transistor, the value of beta is around 30 minimum and often exceeding 100. So the base current is small with respect to the collector current. The input signal's power is equal to the change in Vin times the change in IB. We say change in because that's the portion of the voltage and current that the information of the signal is contained in. We also note that the output voltage is proportional to the output resistance. So let's add a load resistance RL to our output, something that needs to be driven by our transistor circuit. For simplicity, we'll connect the load from the collector to the plus 12 volt rail. So the output voltage is now reduced from IC times RC to IC times the parallel combination of RC and RL. But because of the exponential, we can still set up the system for positive voltage gain, assuming a high enough VBE. The load will draw current IL from our transistor output. Now that we have an output voltage and output current, we can formulate the output signal's power, which is equal to the change in VRC times change in IL. So, with a high enough starting VBE, we can construct a circuit that produces a higher output signal power than input signal power. This is something a transformer cannot do, as the voltage amplification that a transformer provides comes at the cost of attenuating the current proportionally so that the transformer never outputs more power than its input.
So, this circuit can produce power amplification, which is the cornerstone of all electronics. With power amplification, we can convert small signals into much larger signals that can drive other circuits, facilitating the preservation and distribution of information from one circuit to many other circuits. This allows us to create massively complex devices such as ADCs, DACs, and even computer processors.
So here we see the core of why the transistor is so powerful. But there are still a few impediments to us actually using this circuit in some useful way. For one thing, the input voltage is referenced to ground, and the output voltage is referenced to a different voltage rail, which is annoying at the very least. For another thing, this exponential dependency is inconveniently nonlinear. We will start tackling these problems in the next episode of the series when we talk about transistor biasing and the small signal equivalent circuit. That concludes this episode of my transistor tutorial series. In the next video, we will be discussing transistor biasing and small signal analysis. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.